A very good day to everyone. My name is Thurga Devi Munusamy. I would like to share with you my project which has a title of Photoelectrochemical Performance of Phosphorus Doped MoS2 for Hydrogen Evaluation Reaction. First of all, let me give you some brief idea of my project. Due to industrial development and population expansion, the worldwide energy demand increased and it is expected to be doubled by the year 2050. Besides, majority of energy consumption was derived from fossil fuels such as crude oil, natural gas and coal. Unfortunately, combustion of these renewable sources leads to massive pollution and interrupts the ecological system. Therefore, we require an alternative energy, and here it comes the hydrogen that is considered as sacred energy sources, that being an ideal energy carrier. Next, conventionally, hydrogen was produced by steam methane reforming method. However, this traditional technique has some drawbacks. First, the usage of non-renewable sources that is not permanent and will be depleted in the near future. Second, the emission of greenhouse gases, especially carbon dioxide, that giving rise to global temperature and eventually results in climate changes. Okay, next, water electrolysis represent an alternative technology which delivers 4% of the global energy supply. So when we coupled with renewable sources like solar or wind with this technology, it can be treated as sustainable process. And in photoelectrochemical PEC water splitting, hydrogen is produced from water using sunlight and semiconducting materials, which is the catalyst. And this emerging technology is a promising pathway and capable of high conversion efficiency at low operating temperatures. And it can be deduced that this is a long-term pathway with a very low or negligible emission of greenhouse gases. Next, over the past few years, the PEC water splitting gained great attention, which directly converts the solar radiation to hydrogen. And when you see the slide, this system actually consists of anode and cathode immersed in an electrolyte and connected in an external circuit. So typically, the anode or cathode consists of the catalyst and the other side is the metal. And in detail, when the photons, that means the energy from the sunlight, absorbed by the catalyst, the water will split into hydrogen and oxygen through redox reactions, that is two half cell reactions. And the water usually oxidizes at the anode to produce the oxygen gas, whereas at the cathode the hydrogen ions are reduced to produce the hydrogen gas. However, in order for the reaction to take place, the selection of semiconducting materials, that is the catalyst, is very crucial. And in the present work, the phosphorus doped MoS2 was selected and used to evaluate the hydrogen evaluation reaction activity. So in this research, the phosphorus doped MoS2 was synthesized by hydrothermal method and then was subjected to various characterizations. After that, the electrode was prepared by ink brushing technique and the electrode was tested in the PEC system for the hydrogen evaluation reaction activity. Next, the photoelectrochemical PEC activity was conducted to study the hydrogen evolution reactions. So, in the present work, 3-electrode dual chamber was used and connected to the potential state. So, the catalyst represents the working electrode, AgAgCl represents the reference electrode, and the PT wire represents the counter electrode. So, in this work, 0.5 mole sulfuric acid was used as the electrolyte. So this is the results of LSV and TAFEL slope. So the LSV was performed in both dark and light on conditions. As you can see from figure A, the green line shows the lowest overpotential. Generally, overpotential means low overpotential means superior catalytic activity. So the phosphorus doped MoS2 during the light on condition shows great activity. In a similar approach, TAFEL slope was plotted, and the TAFEL slope usually used to interpret the mechanism involved in the hydrogen evolution reaction. So the pure MoS2 is high in both dark and light illumination conditions, that is 137 and 131 respectively. And light on condition, during the light on, the catalyst usually generates more charges and contribute to HER activity. So when you see the phosphorus doped MoS2, the TAFEL slopes are much smaller, that is 90 and 86 in the dark and light on conditions respectively. Thus, we can say that the smaller TAFEL slope, the faster the charge transfer rate in the electrode. That means the P doped MoS2 is much better. In conclusion, the phosphorus doped MoS2 was successfully synthesized by hydrothermal method and then characterized by various analyses, and also tested in the PEC system to evaluate the hydrogen evolution reaction activity. So the present work conveying that the phosphidation of MoS2 able to boost the photoelectrochemical HER activity. That's all from me. Thank you so much for your attention.